All right, so we have a wind-driven ice boat, has a mass of 400 kilograms. The boat starts from rest and reaches a speed of 16 meters per second after traveling a distance of 60 meters. The coefficient of kinetic friction between the ice and the runners of the boat is 0.100. So anytime they give you the coefficient of friction, we know that we're also dealing with probably the formula friction equals mu Fn, which in these problems can usually be written as friction equals mu mg, because the normal force equals the weight and weight equals mg. And I told you that normally when you write the equation, let me start with the equation here. So when you write Ko plus UO, now, so I only write it once. I am going to refer here that where the coefficient of friction would be a negative work, so the work due to friction, that's going to be a negative work. And then the work due to the wind, that's going to be a positive work, because that's really what's making our ice boat move. And so that's going to equal Kf plus Uf. Now, I've told you in the past that you don't even have to know what the mass is if work isn't involved in the problem, because both kinetic energy and potential energy have mass in it. So if the only thing left in your equation are kinetic energies and potential energies, the mass will cancel out. But if work is there, a lot of times you can't cancel it out. So I need to know what the mass is. So the fact is, in this problem, even though I'll know that answer in terms, let me do this. I'll know this number in terms of the mass. I'm not going to know that answer in terms of the mass. So I do need the mass in this problem. And that's the unknown. Determine the work done on the boat by the wind. So there's my unknown. Well, let's see what we can cancel out as zero. If we're on ice, ice is a level surface. Ice freezes horizontally. So that means that in this problem, there is no potential energy. So we can eliminate both of those. We also know that the boat started from rest. So if it started from rest, then it didn't have any kinetic energy to begin with, so that's zero. So now we're down to three variables. And so if I want to solve for the work done by the wind, I just need to move this to the other side. So my equation is going to be the work done by the wind is going to equal, now, since they're giving me mass and since they're giving me the mass and the velocity, I'm not going to write it as K. I'm going to replace this right now with 1/2 mv squared. So 1/2 mvf squared. Now, the work due to friction was actually, I didn't show it here as a negative, but this amount of work right there is a negative because that's limiting the energy that we have. It's reducing the energy. So it's a negative, like I can put the negative wherever I want here. I could still call that positive, but know that that's a negative. When I move this to the other side, it would then be positive. So I'm going to write it as a positive because I'm not going to put another negative sign in it. The wind has to overcome the friction in order to move it off. So it's definitely going to be a positive amount of energy. So I'm going to write that as the work due to friction is going to be mu mg. Now that's the force. That basically, this thing right here is the friction times the distance through which that force acts. So times d. So there's your equation. And I should know everything there in order to solve for the work done by the wind. So the work done by the wind is going to be 1/2 m vf squared plus mu m g d. So I put parentheses for everything that I have to replace, and I think I know everything there. So the mass is 400 kilograms. So that's going to go right there, and that's going to go right here. The coefficient of friction is 0.10, so that's going to go, there's the mu, that's going to go right here. So 0.100. the velocity is 16 meters per second. So it goes from 0, that's why the original kinetic energy was 0, and reaches a speed of 16 meters per second after traveling a distance of 60 meters. So 16 meters per second is my final velocity, so that's going to go right there. So that's 16 meters per second. And the d, that's the distance. So the 60 meters is going to go right there. You see, there's the d there. So that's where I plug it in. So 60 meters goes there. And g, the only thing left is g, and that's 9.8 meters per second squared. Remember that when this work was on that side of the equation, it was a negative work. I moved it over, which now makes it positive, but it was a negative on the other side. I wrote it generically as a positive, but I was keeping track of the fact that I knew this number was negative work. Because, when I'm just writing the formula, I don't know what's positive and what's negative. I know there's two works, and I'll figure that out later. So if you substitute all these, if you do the calculation to solve for the work due to the wind, the answer came out to be, to 3 significant digits, it should have been what? 7.47 times 10 to the 4th joules. Correct? So if you looked at, there's not a lot of work, right? There's not a lot of work. You've got your law of conservation of energy equation combined with the work energy transfer theorem. Then you replaced the K and this with, the variables that create the work, create the kinetic energy. Then we just substitute it. All right, anything else?